Hi everyone. Hi everyone. Hi, hi everyone. I'm Faiulla from RGR Academy. In last session, we discussed about work and relation between work and energy, and some problems about conservation of energy. And now we are going to discuss about the remaining concepts in work energy, like work energy theorem. These all things. Okay. Anyhow, welcome to RGR Academy. So we are located in Chennai. In Chennai, throughout the Chennai, we have various branches, number of branches. We are offering JEE coaching long term for 2 years, NEET coaching for 2 years long term, or NEET coaching for droppers batch, and also NEET coaching for crash course short term batch also. So those who are interested, they can visit the nearest branch of us, or the description given here you can go through, or if you any queries you can ask through the number given in the description. Okay, then we are starting the problems. As we know that work energy theorem, according to work energy theorem, work done by all forces is equal to change in kinetic energy. Work done by all forces is equal to change in kinetic energy. So we are using this point, work done by all forces is equal to change in kinetic energy, to solve some problems which they are asking frequently in NEET and JEE exam, those type of problems. First question: a force acts on a 3 grams particle. A force act on a 3-gram particle in such a way that in such a way that in such a way that position of the particle position of the particle as a function of time is given by x is equal to 3t minus 4t square plus t cube, where x is in meters, and t is in seconds. Find the work done by the force, or find the work done in the first during the first 4 seconds, first 4 seconds during the first 4 seconds. So this is the question. A force acts on a 3-gram particle. The mass is given. Mass is equal to 3 grams in such a way that position of the particle as function of time is given as, they gave us position x is equal to 3t minus 4t square plus t cube, where x is a position in meters, t is time in seconds. Find the work done during the first 4 seconds. So from the time t is equal to 0 up to time t is equal to 4 seconds, we need to find out what is the work done. Okay, so it is not a force, right? So if we know the force equation, if this equation is force equation, we can find out the work done, but it is not force equation, it is the position equation. From position equation, we need to find what is the work done. So from position equation, we can't directly find. So what we have to do is, we need to apply the work energy theorem. So according to work energy theorem, work done by all forces is equal to final kinetic energy minus initial kinetic energy. Work done by all the forces. Okay, that is only we need to find. Half m mass is 3 grams, 3 into 10 to the power of minus 3 kg. It can be common v square minus u square. Final velocity minus final velocity v and u values we need to know. So how to find out v and u? To find out v and u, first we need to find out the equation for velocity. What is the equation for displacement or position? X is equal to 3t minus 4t square, 3t minus 4t square plus t cube. From here, we can find out the velocity equation. Velocity is equal to dx by dt, a differentiation of time with respect, this differentiation of this position with respect to time. So 3t differentiation 3, 8t plus 3t square. This is the velocity equation. If we substitute time t is equal to 0, then we will get initial velocity. At time t is equal to 0, u is equal to 3 minus 8 into 0 plus 3 into 0, we will get initial velocity as 3 meters per second square. Final velocity v is equal to 3 minus 8 into final velocity at time 4 seconds, 8 into 3 plus 3 into 3 square. So in this equation, we are substituting 3 minus 8 into 3 plus 3 into 3 square. So V is equal to 3 minus 24 plus 27, right? 3 cube, na? 27. So we will get here plus 3 plus 3, 6. 6 meters per second. So final velocity is 6 meters per second, 6 square minus initial velocity u is 3 meters per second, 3 square. So work done will be half into 3 into 10 to the power of minus 3 into 6 square, 36 minus 9. So work done is equal to 3 into 10 to the power of minus 3 by 2 into 36 minus 9 will be 27. That's it. A calculation. Simplification, do the simplification. 1.5 into 10 to the power of minus 3 into 27. So if we do the simplification, we'll get the answer. In this way, we can find out the work done by using the velocity concept. We know that velocity, position and velocity relation. So they may ask work done. They may ask work done by giving the position equation also, not only force equation every time. Okay. I hope you understood. We'll go for the next question. An object of mass 5 kg, an object of mass 5 kg is acted upon by a force, is acted upon by a force that varies with position, that varies with position of the object as shown. If object starts from rest, if object starts from rest at x is equal to 0, what is its speed at x is equal to 50? What is its speed at x is equal to 50 meters? The graph given is force and displacement graph, force in newtons, displacement in meters. 25, 50, 10. So this is the question they gave us. They are asking us an object of mass 5 kg, the mass is 5 kg, is acted upon by a force that varies with position. So here they didn't mention any equation for force, but force varies with the displacement. They gave us graph as shown. If the object starts from rest at x is equal to 0, what is the initial velocity? 0 meters per second, because it is starting from rest. What is its speed at x is equal to 50 centimeters? What is its speed at x is equal to 50 centimeters? 50 meters, sorry, 50 meters. So this is what they asked us. So we need to find out velocity, final velocity. To To solve this, we have to apply the work energy theorem. According to work energy theorem, work done by all the forces is equal to half m into v square minus u square. Work done. How to find out the work done? We can find out the work done by finding the area under the curve of force and displacement. So it is looking like a rectangle and triangle. What is the area of a rectangle? Length into breadth, 10 into 25, 250. Half BH, half into base is 25, height is 10, 25 into 10, 250 by 2, it will be 125. This is the area under the curve, 250 plus 125. So totally 375. 375 joules is the work done. So in this manner, we will find out the work done. Work done is nothing but area under the curve. So work done is 375. That is equal to half into mass. How much mass? Mass is 5 kg. They gave in the question. V square minus u square. V square. V only we need to find out. U is already 0 because object is starting from rest. V square minus u square is 0. So 375 divided by 5 into 2, that is equal to V square. V is equal to square root of. So cancel this. 7 times, 5 times, 75 into 2, which is nothing but square root of 150. 50 only, square root of 150. So velocity is square root of 150 meters per second. So in this manner, whenever they gave us some graph or equation of force or position equation, then what we will do? We will find out the work done by the regular method, and then after finding the work done, we will substitute in the work energy theorem. So by work energy theorem, we can find out what is the final velocity. Okay, we go for the next question. A vehicle of mass 10 kg, a vehicle of mass 10 kg is moving in x direction with constant speed of is moving in x direction with constant speed of 10 meters per second. It is subjected to a retarding force. It is subjected to a retarding force F is equal to 0.1 x joules per meter during travel from x is equal to 20 meters to x is equal to 30 meters. Evaluate final kinetic energy. Final kinetic energy. A vehicle of mass. So there is a vehicle of mass. There is a vehicle. Its mass is 10 kg. is moving in x direction with constant speed of, with constant speed is constant, with constant speed of, so initial velocity is 10 meters per second. It is subjected to a retarding force. Retarding force means some resistance force is subjected to a retarding force, opposing force. That opposing force is 0.1x in opposite direction only. Na? During the travel from x is equal to 20 meters to x is equal to 30 meters. So not every time it is from x is equal to 20 meters to x is equal to 30 meters only, this retarding force applied. Then evaluate final kinetic energy. Evaluate final kinetic energy. So how to find out the final kinetic energy? So whenever they give graph or equation of force, equation of position, just remember that we will apply the work energy theorem. According to work energy theorem, work done by all forces is equal to change in kinetic energy, final kinetic energy minus initial kinetic energy. Okay. Net work done. How to find out the net work done? Net work done means work done by all the forces. How many forces are acting work? Sorry, doing work? Only one force. This force only doing work. That work is in opposite direction. So work will be negative value minus F is equal to 0.1x. So that is a force. We know that work done is equal to integral F dot dx. Work done is integral of force into dx. So minus, because it is on opposite direction, minus F, force is 0.1 x. This is the force they gave, F dot dx. From, it is starting from 20 meters to 30 meters. It is acting from 20 meters to 30 meters only. So this is the work done. Final kinetic energy only they are asking. Minus initial kinetic energy. Initially, is it having any velocity? Yes, it is having velocity. So initial kinetic energy is half into mass is 10 kg, velocity is 10 meters per second. Okay. So only unknown thing is final kinetic energy only. Okay, we will find out. Minus integral 20 to 30 0.1 x dx is equal to final kinetic energy minus initial kinetic energy half into 10 into 10 square. Okay, integral of x is nothing but x square by 2. 0.1 is constant, 0.1 into x square by 2. From the limits 20 to 30, as we know that it is negative, it is opposing force, is equal to final kinetic energy minus, so how much we will get here? 5 into 100, 500 joules. So substitute the upper limit now. Upper limit is 30. So minus 0.1 30 square by 2 minus 20 square by 2 is equal to final kinetic energy minus 500. So minus 30 square 900, 900 by 2 450, 450 into 0.1 45 minus 400 by 2 200, 200 into 0.1 20 is equal to final kinetic energy minus 500. Final kinetic energy is 45 minus 20 is nothing but 25 minus 25. Send this 500 to other side plus 500. So final kinetic energy is 500 minus 25, 475 joules. So final kinetic energy is 475 joules. In this manner, whenever they gave in the question this force equation, whenever they gave force equation in the question, this is how we will solve. Work done is equal to change in kinetic energy. Force equation, so work done is equal to integral lower limit to upper limit f of x dx function. Okay, I hope you understood. Okay, we'll move to the next question. 300 joules of work is done by 300 joules of work is done by sliding 2 kg block up an inclined plane, sliding 2 kg block up an inclined plane of height 10 meters, of height 10 meters. Find work done against the friction. Find work done against the friction. Find the work done against the friction. So there is a 2 kg block. Height they mentioned 10 meters. Okay. 300 joules of work done in sliding the 2 kg block up. So to move this 2 kg block upwards, how much work they had done? So work, external work done is 300 joules, done by sliding 2 kg block up an inclined plane of the height 10 meters. So height 10 meters. Find work done against the friction. Find work done against the friction. So these conditions also, what we have to do is we need to apply work energy theorem. According to work energy theorem, work done by all forces is equal to change in kinetic energy. Here, not change in kinetic energy. Here the change is potential energy. It is changing the potential energy, right? It is changing the potential energy, mgh. It is gaining the potential energy, not kinetic energy here. Okay, the change in kinetic energy only we can write here mgh. It is acquiring potential energy. So work done by all the forces. What are all the forces here? So if we draw the free body diagram, we can see what are the forces. What are the forces? First one, weight. Weight is acting downward direction, mg. Next, this is the plane. No? Weight is mg acting downward direction. Then normal reaction force perpendicular to the plane. Friction, it is moving upwards, so friction will be in opposite direction. Some external force, due to the external force, work done already they gave. Okay, this is what are the forces acting. Okay, first work done by weight, work done by mg, plus work done by frictional force, plus work done by normal reaction force, plus work done by external force is equal to gain in the energy mgh. Work done by weight. What is the work done by weight here? Weight is acting downward direction. Displacement is in upward direction. Weight is downward direction, mg. Displacement is in upward direction, 10 meters. Both are in opposite direction. So work done will be negative work done. So minus work done formula minus mg, mass is 2 kg. Yes, 2 kg, mg 10, height 10 meters. Negative work done because both are in opposite direction. Plus work done by friction. Work done by friction only they are asking, work done by or work against the friction. Okay, work done by friction. Plus work done by normal reaction force. So if you observe that displacement, okay, work done by normal reaction force. So if you observe that the displacement, this is the displacement and normal reaction force both are perpendicular to each other. So what will be the work done by normal reaction force? It will be 0. Plus, what is other thing remaining? Work done by external force, that is they gave here 300 joules. Work done by external force is 300 joules. That will be is equal to mgh. mgh, change in the energy, or directly we can write mgh, actually, so we can write here mgh, change in kinetic energy. No? Okay, we'll write that. Change in kinetic energy will be 0. In other manner, we can say that initially it is at rest, finally it is at rest. Okay. Done. So that will be is equal to 0. So if we solve that, then we will get work done by frictional force. So there are two ways. Either you can take here mgh, that is one way. Other way is you are taking here 0, then we have to consider work done by gravitational force. If you are not considering work done by gravitational force, then you have to consider here mgh, it is acquiring mgh. So what is the answer we will get? Work done by frictional force, it will be, here we will get 200 plus 300, 100. So minus 100, frictional force, work done by frictional force is minus 100 joules. Okay. Okay. So we'll move to the next question. A particle of mass 10 grams, a particle of mass 10 grams moves along a circle of radius, moves along a circle of radius 6.4 centimeters with constant tangential acceleration, with constant tangential acceleration what is the magnitude of this acceleration? What is the magnitude of this acceleration if kinetic energy of the particle becomes, if the kinetic energy of the particle becomes 8 into 10 to the power of minus 4 joules by the end of second revolution, by the end of second revolution. By the end of second revolution, after beginning the motion, after beginning the okay, this is the question. This is the question from our side. So from our side, from my side, I'm giving you this question to solve this question, and those who send the correct option, correct answer for the given description number, they will get either NEET material or JEE material, whatever the material you need. So from our side, from RGR Academy side, we are going to present you those who gave the correct answer for this question. Okay, just see here. Once again, I will read the question. A particle of mass 10 grams moves along a circle of radius 6.4 centimeters with constant tangential acceleration. What is the magnitude of this acceleration if the kinetic energy of the particle becomes 8 into 10 to the power of minus 4 joules by the end of second revolution after beginning the motion? Hope you will do, and you will send the correct answer. Okay, next question. Consider a drop of rainwater. Consider a drop of rainwater having mass 1 gram, having mass 1 gram, falling from a height of 1 kilometer, falling from a height of 1 kilometer. If it hits the ground with a speed of, it hits the ground with a speed of 50 meters per second, find the work done by gravitational force. Find the work done by gravitational force. Resistive force of air. Resistive force of air. Consider a drop of rainwater having mass 1 gram. So mass of the rainwater 1 gram, falling from a height of 1 kilometer, falling from a height of 1 kilometer, 1 into 10 cube meters, and 1 gram na 1 into 10 to the power of minus 3 kg. We are writing in SI system, nothing else. It hits the ground with a speed of 50 meters per second. So while it is hitting the ground, so final velocity V is equal to 50 meters per second. Find the work done by gravitational force. The first question they are asking us, what is the work done by gravitational force? So what is the work done by gravitational force? So gravitational force is nothing but weight only, mg. And displacement in which direction? Displacement also, the raindrop is falling in downward direction. The displacement also downward direction, yes. So work done is equal to force into displacement. Force is mg, displacement is s, both are in same direction, so positive. So work done is equal to mass 1 into 10 to the power of minus 3 kg, g value 10, displacement 1 kilometer, 10 cube meters. So work done by gravitational force, we can say that 10 to the power of minus 3 plus 3 cancel, 10 joules. So this is the work done by gravitational force. Work done by gravitational force. First question completed. Second thing, what is the work done by resistive force? So here we have to apply the work energy theorem. According to work energy theorem, work done by all the forces is equal to change in kinetic energy, final kinetic energy minus initial kinetic energy. Work done by all forces. What are the forces on the raindrop? This is the raindrop. Its weight is the force, one force. Another force, they are mentioning that there is a resistive force. So while it is falling down, there will be a resistive force acting upward direction. Resistive force in upward direction. But the displacement downwards only. Displacement is 1 kilometer downwards. So work done by all the forces. One is work done by gravitational force plus work done by resistive force is equal to change in kinetic energy half m into v square minus u square, final velocity v square minus initial velocity u square. Work done by gravitational force, already we know it, 10 joules. Work done by resistive force, that is equal to half into mass value. Mass, how much they gave mass? 1 into 10 to the power of minus 3 kg into velocity, final velocity. While it is hitting the ground, what is the velocity? While it is hitting the ground, velocity is 50 meters per second. 50 meters per second minus initial velocity, it is just a falling, free falling body. So initial velocity will be 0. So 10 plus work done by resistive force or resistance force is equal to 50 square 2500, 2500, 2.5, 2 point, okay, 2500 into 10 to the power of minus 3 by 2, where we will get 2.5 by 2, 2.5 by 2. The work done by resistive force is equal to 2.5 by 2 minus 10, which is nothing but minus 2.5, 1.259, 1.25 minus 10 minus 8.75 joules. Minus indicating that, as we know now, resistive force and displacement opposite to each other. Okay, I hope you understood. Just once again, go through the question. A raindrop is falling from a height, free falling object, falling from a height 1 kilometer. It hits the ground with a speed of 50 meters per second. Find the work done by gravitational force, the resistive force of the air. Next question. An object of mass m is tied to a string of length L. An object of mass an object of mass m is tied to a string of length L, and a variable force F is applied on it, and a variable force F is applied on it which brings the string gradually at an angle theta to the vertical, which brings the string gradually at an angle theta, gradually to an angle theta with the vertical. Find work done by force F. Find work done by force F. Find work done by force capital F. An object of mass m is tied to a string of length L, and a variable force capital F is applied on it, in which brings the string gradually to an angle theta. So they mentioned the diagram also in the question. The force is horizontal force. So this is the initial position of the mass. After applying some force, gradually it is making an angle theta. This is the final position, theta. It is making an angle theta with the vertical. Find the work done by force. Find the work done by force. Find the work done by force. How to find it? See here, it is very simple question, but somewhat lengthy. So due to work done, this is the height, or this is something h, it is displaced. This is the displacement. Why we need displacement? We know that work done is equal to force into displacement. Work done is equal to some external force F is applied, it is okay, into displacement. How much displacement it is? H. So what is this force F in terms of mass? Because they only gave mass in the question, and also they gave the length in the question. So in terms of length, what is this H value? First thing, in terms of length, what is H value? And second thing, in terms of mass, what is the force? If we can Find and substitute these values here, we'll get the answer. So okay, force, how to find out the force? Force is equal to, so if we draw the free body diagram, downward there is a mg, weight acting, right? Okay. Okay, we'll try to apply the work energy theorem. Work energy theorem, work done by all forces is equal to change in kinetic energy. Work done by external force plus work done by gravitational force is equal to change in kinetic energy. Kinetic energy change is 0 because initially it is in rest, finally also it is in rest. Work done by external force, how much displacement it created, how much displacement it created in the direction of force. What is the displacement? It is lifting the height of h. What is h value? If we know this value, we can find out the h value. So how to know this value? So this total length is l. L minus this h dash, then we will get h value. H minus h dash, sorry, L minus h dash, then L minus h dash is equal to h. L minus h dash. What is h dash value? If you observe, this is a right angle triangle. This is hypotenuse L. So h dash is equal to L, adjacent side only na, L cos theta we will get. H is equal to L cos theta. L cos theta. This is the work done by gravitational force. The work done by gravitational force. Work done by gravitational force is what we said now. Uh, H lifted. So mg into, this is the force. Force into displacement. Displacement is h. H value is L into L minus cos theta. L into L minus L cos theta, right? So L. So this is work done by gravitational force. What is the work done by applied force? So this is the direction of applied force. So how much it is lifted? But in this direction, what is the displacement? According to this, we can say that displacement is 0. Actually, force and displacement are perpendicular because it is lifting height, and force are perpendicular. So we can say that it is nothing but 0. Or let it be work done by external force. Work done by external force is equal to mg into L minus L cos theta. Okay, mg L into 1 minus cos theta. Okay, sorry, it is not lifted, but it is pulled some distance. So there will be some work done in the direction of force. So we can say that it is not 0. Wf, change in kinetic energy, is 0. In this manner, we can find out work done by external force, applied force. Okay, so this is by applying the work energy theorem. Without applying work energy theorem, directly applying the formula for work done, here also we can find out. But we don't know na f value, so that's why we need to know f value. So we can't apply the direct formula directly. By using work energy theorem, we can find out work done by some external force plus work done by gravitational force is equal to change in kinetic energy. Change in kinetic energy is 0. Next question. System is released from rest with the spring unstretched. System is released from rest with the spring unstretched. With the spring unstretched. The maximum extension of the spring is, the maximum extension of the spring is, They gave one diagram also here. A spring constant K here, and a mass A here, and its mass is M, and one more mass 2M attached here. So this is a system they gave. This is an unstretched condition. Unstretched condition. System is released from rest. So initially it is unstretched condition with the spring unstretched. Sir, spring is unstretched. The maximum extension of the spring is, if once it is released, then what is the maximum extension of the spring? So see here, in this system, if we release it, the mass 2m is more. Anyhow, there is no mass here. So mass effect here, it won't affect anything if it is a smooth surface. Na? So what happens is it will go down. This 2m mass will do some work. That work will, the same amount of work will stored in the form of potential energy of the spring. So how much displacement it make? If we know that, we can find out what is the spring extension x value, because whatever the work done here, whatever the work done here, that will be stored in the form of potential energy in the spring. How to find out the work done? Work done is equal to force into displacement. So on this system, which force is working? Which force is doing here? So this 2m, weight of the 2m mass, pulling the whole system downwards. So 2mg is the force. So due to 2mg, this whole system will move downwards. So suppose it is displaced by x. The same amount only na spring will stretch, because this everything is attached. So if the system, this mass is going down a x displacement, the spring also should extend x. So potential energy stored inside the spring is half kx square. Half kx square. So whatever the work done by the system, that will be stored in the form of potential energy of spring. Work done by the system, work done is equal to force into displacement. This 2mg is the force pulling the system downwards. Due to that, the whole system is displacing x distance downwards. Spring also extended by x. So extension of the spring also x. Okay, this mass also move x distance. This mass also move x distance. Everything displaced by x distance. So spring also extended by x distance. Work also force into displacement x. So if we solve this, we can find out the x value. X value only they are asking. The maximum extension of the spring. X is equal to 4 mg by k. X is equal to 4 mg by k. Okay, this is how we will find out this spring connected masses. Spring connected masses. Next question, find the maximum compression of the spring would be. Find the maximum compression of the spring. They gave one diagram for us. We need to solve that. So there is a spring attached here, and its spring constant 15 Newton per meter, and there is a mass. It is a smooth surface. They mentioned here it is a smooth surface. On the smooth surface, 0.5 kg mass is moving with a velocity 1.5 meters per second. It is moving with a velocity 1.5 meters per second. So what will be the compression of the spring? Actually, we can say that maximum compression of the spring. Okay, initially, is there any energy inside the spring? Potential energy stored in the spring is 0. After some time, it is compressing. If it is compressing maximum, then what happens is it is gaining some energy. It is gaining some energy from this object, because this object is initially having, so initial energy is this object having kinetic energy of the mass half mv square. Half mass is 0.5 kg, velocity is 1.5 whole square. This is the kinetic energy. This whole kinetic energy is converted into potential energy of the spring. What is the formula for potential energy of the spring? Half kx square. According to conservation of energy, whatever the energy initial here, that should be final energy. Initially it is kinetic energy, finally spring is compressed. So which type of energy it is? Potential energy of the spring. So these two should be equal in case of maximum compression. So kinetic energy half 0.5 into 1.5 whole square, it should be is equal to half into k value. What is spring constant? 50 into x square. Okay. So 0.5, 0.1 here, 10 here, 10 to the power of minus 2 into 15 square is equal to x square. So x is equal to what we will get now? 15 into 10 to the power of minus 1. X is equal to 1.5 meters. So this is the maximum compression of the spring. Okay. So in this manner, we can apply the conservation of energy theorem. So initially, this object is having kinetic energy. The total kinetic energy is converted into potential energy of the spring without any loss. Without any loss. So that's why kinetic energy of the mass initially is equal to potential energy stored inside the spring. Okay. Okay. I hope you got some idea on these type of problems, conservation of energy and also work energy theorem. Okay, I hope you enjoyed. As I said, we are from RGR Academy. We are located in Chennai. We are offering all the type of coachings like NEET coaching, NEET long-term, short-term coaching, and also JEE 2 years coaching, simultaneous coaching with the school for JEE. Okay, and also NEET also for 11th and 12th class students. We are located overall all of the Chennai. We have centers throughout the Chennai. So for any type of coaching, you can contact the given number below in the description. Okay, thank you.